Welcome back to QHSE Talks. And today is not just another episode. This is the starting point of a complete journey. We're kicking off ASP 11 Domain 1, and this is Episode 1, Calculating Storage Capacity. But what we're really building here is something much bigger. Over the next 16 episodes, we're going to walk through the full mathematical foundation of safety, step by step, from storage and rigging to heat stress, fall protection, exposure limits, even financial decisions. Not as isolated formulas, but as a system that controls how safe or how dangerous an operation really is. Because in safety, we don't calculate numbers just to get answers. We calculate to define limits. Limits that separate normal operation from failure. And throughout this series, you'll start to see how every equation connects to a real decision, how the ASP exam expects you to think, and more importantly, how small mistakes, a wrong unit, a missed factor, a simple assumption, can lead to consequences far beyond what the numbers suggest. Because when you really stop and look at any structure around you, any warehouse, any tank, any building, what you're actually looking at is not just steel and concrete. You're looking at something that is only stable because it has been precisely calculated to stay that way.
And the only thing keeping that building from literally tearing itself apart, or the ground from opening up beneath your feet, is the math done by a safety professional long before the first foundation was ever poured.
It really is the hidden architecture of the modern industrial world. I mean, we interact with these spaces completely oblivious to the fact that every square inch,
Every single one.
every volume of liquid, every stacked pallet has been aggressively calculated, challenged, and constrained by regulatory math.
Right.
It's not abstract at all. It is the absolute definition of high-stakes calculations. Like, the math doesn't just describe the physical world here, it actively restrains it.
And that restraint, that mathematical barrier between operational success and a total catastrophic failure, that is the entire mission of our deep dive today.
And we have some heavy-duty materials to go through.
Oh, we really do. We are pulling from a stack of highly technical, frankly intimidating sources. We've got the Board of Certified Safety Professionals, specifically the BCSP preparation questions.
Those are no joke.
Not at all. We're integrating structural notes from QHSE Talks, and we are laying all of that over the rigid, unyielding legal frameworks of the OSHA and EPA handbooks.
The law.
The law. And we are looking specifically at ASP Domain 1, Topic 1, Calculating Storage Capacity.
Which, to anyone outside the field, sounds like a completely straightforward, maybe even dry exercise, calculating storage capacity.
It sounds like middle school geometry.
Right. You measure a box, you find out how much fits in the box, done.
Right. But anyone prepping for the Associate Safety Professional exam knows that the quote-unquote box is actively trying to destroy the facility.
It really is.
So whether you are studying to pass that exam, or you are an engineer, or just someone who's insanely curious about how we manage catastrophic risk at scale, this topic fundamentally changes how you view a physical space.
Completely.
Because when you synthesize all these study guides and regulatory codes, they are just asking you to find geometric volume. They are forcing you to find the volume available for safe storage.
And the delta between the theoretical geometric volume and the safe operational volume, that is where disasters happen.
That's the danger zone.
Exactly. If you miscalculate that delta, you aren't just getting a red mark on a test. You are overloading a floor slab until it literally shears.
Or overfilling a chemical reactor until it vents toxic gas right into a neighborhood.
Right. The exam is testing your ability to bridge the gap between ideal mathematics and a very messy, highly unpredictable physical reality.
Okay, let's unpack this. To build that bridge, we obviously have to start with the raw geometry.
Right. Physical bounds of the space.
Right. But looking at the source materials, it's pretty clear that the exam doesn't just hand you a neat, easily identifiable shape.
Oh, never. That would be too easy.
The first real hurdle a safety professional faces out in the field, or, on a test question, is properly identifying the container and applying the correct spatial relationship.
Because the math scales in ways that aren't immediately intuitive to most people.
That's the critical piece. Let's talk about the shapes. We're dealing with three primary architectures here.
Right, you have the rectangular prism, the cylinder, and the sphere.
Let's start with the rectangular prism.
So that is your standard warehouse, your indoor storage room, or maybe an outdoor concrete containment berm.
And the volume formula for that is just length times width times height.
Exactly. It's completely linear. So if you double the length of a warehouse, you literally just double its volume.
Which is easy enough to mentally track. Like, I can picture that in my head.
Sure.
But the industrial world rarely relies on boxes when it comes to volatile materials.
No, a box is a terrible shape for pressure.
Right, so we use cylinders, storage tanks, mixing vats, pressurized gas lines. And the math for a cylinder pie times the radius squared times the height, that behaves very differently.
It does, and that's a huge trap for those who aren't really thinking about the physical implications of that formula.
Walk us through that. Why is it a trap?
Well, because the radius is squared, so the volume doesn't scale linearly with the width of the tank. It explodes geometrically.
I really want to highlight that because it's a vital concept in the sources. Let's say a facility manager decides they need to upgrade their chemical storage, right?
Okay.
And they replace a tank with one that is exactly twice as wide. So they double the radius. They haven't just doubled their storage capacity, have they?
Not at all, because that radius is squared in the formula. Doubling the width actually quadruples the volume.
4 times the amount.
Exactly. And that means you have quadrupled the weight, you've quadrupled the potential fire load, and you've quadrupled the required secondary containment.
That is massive.
I've seen real-world risk assessments just fall completely apart because a planner intuitively assumed that a slightly wider tank would only bring a slight increase in risk. The geometry punishes that kind of linear thinking.
It's like baking a cake.
How so?
Well, if you misjudge the volume of the pan, you get batter burning on the bottom of your oven.
Oh, right. Yeah.
But in the industrial world, using the wrong equation means your risk assessment is fundamentally flawed. And instead of burnt cake, you get a toxic spill.
That is a very accurate, if slightly terrifying, analogy. And it gets even more nuanced depending on orientation.
Orientation, like standing up versus laying down.
Exactly. A vertical tank uses that standard formula we just talked about. But if you take that exact same cylinder and lay it horizontally, like a massive propane bullet tank, you're swapping height for length.
So it's pi times radius squared times length.
Right. It's the same core math, but the risk profile completely changes.
A volume is the same.
Because a horizontal cylinder distributes its weight across a much larger footprint. A vertical tank concentrates that massive quadrupled weight onto a very, very tight foundation.
Oh, wow. So the concrete beneath a vertical tank is under way more stress than the concrete under a horizontal one, even if they hold the exact same amount of liquid.
Precisely. Then you move into the specialized realm of high-pressure storage, which requires spheres.
The giant golf balls.
Right, exactly. And the volume of a sphere is 4/3 times pi times the radius cubed.
Cubed. So now we aren't just squaring the growth.
No, we are cubing it. Spheres are used for highly volatile pressurized gases like LNG, liquefied natural gas.
Why a sphere, though?
Because a sphere distributes internal pressure perfectly evenly across its entire surface area.
Oh, because there are no corners.
Exactly. There are no corners for the stress to concentrate on, but because the radius is cubed, even a tiny miscalculation in the physical measurement of that sphere results in a massive discrepancy in your volume calculations.
So if your tape measure is off by just a little bit.
If your baseline physical measurement is wrong, every subsequent calculation you make about pressure thresholds, safety relief valve sizing, or emergency venting, it's all built on a mathematical fiction.
But here's the crazy part. According to the BCSP preparation sources, failing to remember the formula for a sphere isn't actually what takes people down on the exam.
No, the math itself isn't usually the stumbling block.
The hidden assassin in these risk calculations, the trap that catches seasoned professionals and exam takers alike, is this fundamental disconnect between the tools we use to measure the physical world and the language of the law.
The unit mismatch.
Yes.
It is the single most common point of failure in capacity calculations, hands down.
Break this down for us because it seems so simple on the surface, but the sources just hammer it relentlessly.
Well, think about the physical act of measuring a facility. You are out in the field with a laser distance meter or maybe a tape measure. You are measuring the length and width of a containment berm or the height of a tank.
Okay.
Your raw data is coming in feet or meters. So when you run your geometric formulas with those numbers, your result is in cubic feet or cubic meters.
Right. So if I have a room that is 10 by 10 by 10, that is 1,000 cubic feet. I have my volume.
You have a volume,
Okay.
but you don't have a legally actionable volume.
Because of the regulations.
Exactly, because when you open up the OSHA handbook or the EPA regulations for spill prevention, control, and countermeasure SPCC plans, those federal statutes do not care about your cubic feet.
They don't use cubic feet.
The rigid legal thresholds are almost universally codified in gallons.
Wow. So the physics is speaking one language and the law is speaking another.
Yes.
If I can't translate my physical cubic feet into regulatory gallons with absolute precision, I have no idea if my facility is compliant or if we are about to be hit with a massive federal violation.
Precisely. And the conversion factor is not a clean, round number.
Of course it isn't.
The standard you must have seared into your brain is that 1 cubic foot equals 7.48 gallons.
7.48. Not 7, not 7.5. It has to be that precise.
It has to be, because at an industrial scale, rounding errors create ghost volume.
Ghost volumes, yeah.
Imagine you have a warehouse containment area that is 100,000 cubic feet,
Right.
and you use 7.5 instead of 7.48 as your conversion.
Okay, let me think. That's a difference of 0.02 per cubic foot.
Right. So over 100,000 cubic feet, you just hallucinated an extra 2,000 gallons of containment capacity that does not physically exist in the real world.
Oh my God.
So if a tank ruptures, those 2,000 gallons are going right over the concrete wall and straight into the local water table, all because of a lazy decimal point.
That is a terrifying thought.
Yeah.
2,000 gallons of toxic chemicals just escaping because someone rounded up.
It happens.
And conversely, if we were working backward from a chemical supplier's invoice,
Yeah.
say they delivered 5,000 gallons of a solvent, and we need to know how much physical space that will take up in our tanks, we need the inverse conversion.
Right, you have to go from gallons back to cubic feet.
And the sources say 1 gallon is equal to 0.1337 cubic feet.
Yes. And for our metric practitioners, the exam frequently tests the transition into liters. 1 cubic foot is 28.317 liters.
That's a mouthful.
It is, but the most elegant conversion, the one that makes metrics so much easier for process engineers, is that 1 cubic meter is exactly 1,000 liters.
Oh, that is so much cleaner.
Metric usually is.
Okay, I want to pull a highly specific scenario straight from the BCSP practice questions to illustrate how this unit mismatch operates under stress.
Let's do it.
Because the exam doesn't just ask you to convert a static number. That would be too simple. It forces you to convert units while accounting for dynamic flow rates and time constraints.
Ah, the dual container fill rate problem. It's a classic for a reason.
It really tests everything, doesn't it?
It tests geometry, conversion, and operational forecasting all at once.
Right. So let's walk the listener through the mechanics of this. Imagine you have a process line filling 2 different containers simultaneously.
Okay.
The flow rate is identical for both, 2.5 gallons per minute.
Got?
Container A is a vertical cylinder. Container B is a rectangular box. Now, the problem doesn't give you their capacity in gallons. It doesn't even give it to you in cubic feet.
Let me guess. Cubic inches.
Yes, it gives you the volume in cubic inches.
Which, by the way, is incredibly common in manufacturing, where you are dealing with machine-tooled parts and smaller buffer tanks.
Exactly. So the cylinder has a known geometric volume of 2,714 cubic inches.
Okay.
The box has a volume of 4,320 cubic inches. The scenario asks you to evaluate the risk state of these 2 containers after exactly 4 minutes of active filling.
If you approach this without a structured methodology, you will fail.
Why?
You can't just look at 2,714 cubic inches and 4,320 cubic inches and compare them to 2.5 gallons. The units are hostile to each other. They don't talk.
Right.
Step 1 is isolating your flow rate unit, which is gallons, and forcing the spatial volumes to match it.
So we need the bridge from cubic inches to gallons.
And the standard U.S. liquid gallon is legally defined as exactly 231 cubic inches. That is your bridge.
Okay, so let's do the math. We take the cylinder first.
Right.
2,714 cubic inches divided by 231.
Which gives you?
That translates to an absolute physical capacity of 11.75 gallons.
Perfect. And we do the exact same thing for the box. 4,320 cubic inches divided by 231 gives us 18.70 gallons.
So now we have finally established the baseline reality of the hardware, but in the language of the operation.
Exactly. We have an 11.75 gallon cylinder and an 18.70 gallon box.
Now we introduce the dynamic variable time. We are pumping at 2.5 gallons per minute for 4 minutes.
Simple math there. 2.5 times 4 is exactly 10 gallons.
So 10 gallons of liquid has been introduced into each system.
What's fascinating here is that this is where the safety professional has to interpret the math, not just solve it.
Right. What do the numbers actually mean?
You look at the cylinder, it holds 11.75 gallons. You just pump 10 gallons into it. You subtract the 2, and you find that this cylinder only has 1.75 gallons of void space remaining.
And at a slow rate of 2.5 gallons per minute.
In less than 45 seconds, that tank is going to breach. It is in a critical redline state.
But the box, which started with 18.70 gallons of capacity, has taken the same 10 gallons.
Right, so it still have 8.70 gallons of void space left.
It could run for over 3 more minutes before reaching critical status.
It's in a safe, green state.
What I love about this problem is that it proves why intuition is so dangerous in engineering.
Oh, intuition will get you in so much trouble.
If you just looked at the raw cubic inches, 2,714 versus 4,320, they both just feel like abstractly large numbers.
Right. Your brain doesn't naturally translate that difference into one is about to spill, the other is completely fine.
Exactly. The math forces the invisible reality right up to the surface.
It strips away all the abstraction. And this micro example of 2 small containers is just the warm-up.
Just the warm-up.
Oh, yeah. The true test of a safety professional is taking this exact same methodology and applying it to a facility that is 1,000 times larger.
Which brings us to the reality of macroscopic space. We've established the math for a theoretical box. But let's scale that box up to a 500,000 square foot logistics warehouse.
That's a big box.
It is. If I'm a corporate planner and I lease a building with 500,000 square feet of floor space and 40-foot ceilings, my spreadsheet tells me I have 20 million cubic feet of geometric volume.
It sure does. And if you try to utilize 20 million cubic feet of that space for actual storage, you will be shut down by the fire marshal, cited by OSHA, and likely cause a structural collapse.
Yikes.
Yeah. This is where the ASP curriculum draws a very hard line between total area and net area.
The theoretical versus the actual.
Exactly. Total area is just the architectural boundary, wall to wall, floor to ceiling. But net area recognizes that a building is not a static void, it is a biological organism.
I like that analogy.
Think about it. The storage racks are the tissue, but the space between them, the aisles, the access points, the clearance zones, that is the cardiovascular system of the facility. If you choke off those arteries just to add more tissue, the entire organ fails.
The sources introduced this concept called the utilization factor to calculate this.
Yes.
The formula is effective capacity equals geometric volume multiplied by a utilization factor. And the standard industry range for this factor is remarkably punishing. It's typically between 0.7 and 0.9.
Which means, right off the top, you are legally and operationally required to surrender 10 to 30% of your geometric volume to empty space.
I can easily imagine a purely profit-driven operations manager looking at that and fighting it tooth and nail. We are paying for that air, pack the racks closer together, shrink the aisles.
Well, they do. They absolutely fight it.
So why is that 30% empty space so non-negotiable?
Because that empty space is heavily regulated safety infrastructure. It's not just air. OSHA mandates a minimum of 3-foot clear aisles for standard human transit.
Okay, 3 feet makes sense for a person walking.
Right, but if you have mechanical material handling equipment like heavy forklifts, those aisles must be significantly wider to account for turning radiuses and load sway.
You can't have a forklift knocking into a rack.
Exactly. Plus, you cannot block electrical panels. And you must maintain 18 inches of absolute clearance below fire sprinkler heads so the water spray pattern isn't obstructed.
18 inches of just empty air at the top.
Yep. And most importantly, egress.
Egress is paramount, right?
It is everything. If a fire breaks out, workers need a clear, unimpeded path to an emergency exit. If you've pushed your utilization factor to 0.95, meaning you've packed the floor to 95% capacity, you have likely created a labyrinth.
Which is terrifying in a smoke-filled room.
Workers get trapped.
Yep.
Furthermore, you fundamentally altered the fire load of the building.
Fire load. That's a crucial concept in the QHSE notes. What exactly is that?
Fire load is the total amount of combustible material in a given space. If you pack pallets too densely, you aren't just creating a labyrinth. You are creating an unbroken chain of fuel.
So the fire just hops from one to the next.
Exactly. When a fire starts, it jumps easily from rack to rack. The heat release rate skyrockets, completely overwhelming the thermal rating of the sprinkler system, and suddenly a localized pallet fire becomes a total facility loss.
Wow.
The utilization factor of 0.7 isn't wasting space, it is a calculated fire break.
That makes so much sense.
Yeah.
But the utilization factor only addresses volume. It only addresses the space the objects take up. We have to pivot now to the other side of the ASP domain 1 coin, which is mass.
Mass and gravity.
Right. Because as we discussed earlier, storage capacity is ultimately a calculation of gravity. It is load risk.
You can have a warehouse with a perfect utilization factor of 0.7, perfectly clear aisles, pristine sprinkler clearance, and still absolutely destroy the building if you don't understand the math of floor loading.
The sources provide a master formula for translating volume into physical weight, and it introduces a variable that catches a lot of people off guard.
Oh, it really does.
The formula is weight equals volume in gallons multiplied by 8.34 multiplied by the specific gravity. Or, if you are working in cubic feet, weight equals volume in cubic feet multiplied by 62.4 multiplied by specific gravity.
Those constants 8.34 and 62.4, they are the anchors of the equation.
Where do they come from?
Well, 8.34 is the exact weight in pounds of 1 single gallon of pure water.
Right.
And 62.4 is the weight in pounds of 1 cubic foot of pure water. Water is the universal baseline for density in industrial engineering.
Which is where specific gravity comes in.
Exactly. Specific gravity is just a ratio. It compares the density of whatever substance you are storing directly to the density of water. So water has a specific gravity of exactly 1.0.
So if I have a chemical that is physically heavier and denser than water, say a concentrated sulfuric acid, it might have a specific gravity of 1.8.
Right, meaning it is 1.8 times heavier than the exact same volume of water.
And if I have a light hydrocarbon, like a refined oil, it might have a specific gravity of 0.8. It's lighter.
Yes, and this is where the subtlety of failure occurs. Let's look at a forensic scenario.
I love these.
Let's say you have a facility storing industrial solvents. For years, they've stored a solvent with a specific gravity of 1.0.
So same weight as water.
Exactly. A standard 55-gallon drum of that liquid weighs roughly 460 pounds.
They put it on a standard pallet. They stack the pallets maybe 3 high on a steel racking system. The racks hold it perfectly. Everything is fine.
Right. But then the procurement department decides to switch suppliers, or maybe they change the chemical composition to a slightly denser industrial cleaner.
To save money or something.
Usually. And the new liquid has a specific gravity of 1.3.
So to the naked eye, it looks exactly the same. It comes in the exact same 55-gallon steel drums. The warehouse workers handle it the exact same way. The geometric volume hasn't changed by a single cubic inch.
Not a bit, but the mass has increased by 30%. That single 55-gallon drum now weighs nearly 600 pounds. So when they stack those pallets 3 high on the racks, the steel beams are suddenly taking thousands of pounds of sheer force they are not engineered to handle.
Does the rack just collapse instantly?
Usually no, it doesn't break on day one. But over 5 years, the massive concentrated load causes microscopic metal fatigue in the rack joints.
And it transfers that force down through the base pleats directly into the concrete floor.
Exactly. This is floor loading. The force is measured in pounds per square foot, or PSF. Every concrete slab is engineered for a maximum PSF.
And if you exceed it,
the concrete doesn't just crack, it shears. We've seen catastrophic incidents where a racking system, overloaded by a subtle shift in specific gravity, suddenly collapses without any warning.
just giving way all at once.
It triggers a domino effect, bringing down an entire aisle of heavy drums, crushing workers, and causing a massive hazmat spill.
This is why the OSHA Construction Handbook has a non-negotiable mandate. The maximum safe load limits of floors must be conspicuously posted in all storage areas.
It's not a suggestion, it is a structural red line.
If the sign says 250 PSF and your math says your densely packed pallets of specific gravity 1.3 liquid are generating 280 PSF, you cannot put them there. The floor will eventually fail.
The exam frequently tests this concept by pushing it to absolute extremes, forcing you to calculate the physical stress of massive volumes. There's a classic example in the study guides regarding elevated water gravity tanks.
Oh, this one blew my mind when I was reviewing the notes. We see these tanks all the time. The massive municipal water towers or the elevated fire suppression tanks right over industrial plants.
Right. They are vital for providing immediate gravity-fed water pressure in an emergency. But suspending that much liquid in the air requires staggering structural engineering.
The scenario presents a 90,000-gallon water tank, elevated 125 feet in the air on a steel superstructure. The question isn't about the volume. It's about calculating the sheer static load acting on that structure.
So we apply the math. We have 90,000 gallons. We know water has a specific gravity of 1.0, and we know our constant is 8.34 pounds per gallon.
Okay, let me do the math. So 90,000 multiplied by 8.34. That gives us exactly 750,600 pounds.
750,000 pounds of dead weight.
Suspended 12 stories in the air. And that is just the water. That doesn't count for the hundreds of thousands of pounds of the steel tank itself, or the massive structural legs holding it up.
And this is where safety engineering heavily intersects with civil engineering. When you calculate a 750,000-pound load elevated 125 feet, you realize that the structure isn't just fighting gravity.
What else is it fighting?
It is acting as a massive pendulum.
Oh, wow.
If you have high wind shear or minor seismic activity, that 750,000 pounds of mass wants to sway. If the foundations aren't engineered to handle that specific dynamic load, the entire tower will literally torque and collapse.
It's deeply humbling to think about the math holding up the skyline like that. But I want to latch onto a word you just used, dynamic.
Okay.
A water tower is mostly static, but in chemical processing, liquid storage is intensely dynamic.
Yeah.
Solid goods on a warehouse rack stay exactly where you put them, but liquid is constantly trying to escape.
Liquid is chaotic. It sloshes, it evaporates, it responds violently to temperature changes, which means we have to move into a completely different tier of risk assessment.
Let's talk about process safety and bulk liquid tanks. If I have a massive cylindrical chemical reactor, why can't I just use our handy formula from the beginning? Volume equals pi times radius squared times height. Find the total cubic footage, convert it to gallons, and say, boom, there is my storage capacity.
Because if you do that, you are calculating the geometric capacity, not the safe operational capacity.
There's that difference again.
Exactly. The ASP sources provide a deeply nuanced formula for process tanks that strips away the theoretical and forces you to deal with the mechanical reality.
What's the formula?
The formula is net capacity equals the open parenthesis, volume minus deadwood, close parenthesis, multiplied by the fill percentage minus the heel.
Okay, there's a lot of specialized vocabulary in there. Let's isolate these variables, starting with deadwood. What is deadwood?
If you calculate the volume using just the outside diameter of a steel tank, you are assuming the tank is a perfectly hollow, empty shell.
Like a giant empty soda can.
Exactly. But in industrial processing, a tank is essentially a machine. It contains massive internal infrastructure.
Right. You might have internal heating coils to keep a viscous liquid flowing. You have massive mechanical agitators and mixing blades. You have internal baffle plates to prevent the fluid from sloshing around. You have dip tubes and sensor arrays.
All of that solid steel and instrumentation takes up physical space. That displaced volume is called deadwood.
Ah, I see.
Depending on the complexity of the reactor, the deadwood can account for hundreds or even thousands of gallons of displaced volume. If you don't subtract the deadwood from your geometric volume, your math says you have room for 50,000 gallons. But the physical reality might only have room for 48,000.
Which means if you try to pump 50,000 gallons in, those last 2,000 gallons have absolutely nowhere to go but out the emergency vents or over the sides.
Exactly. So volume minus deadwood gives us our actual internal void space. But then the formula tells us to subtract the heel.
What is the heel?
It's an operational reality of fluid dynamics. When you drain a tank, the discharge nozzle is almost never perfectly flush with the absolute lowest point of the floor.
Why not?
It's usually raised slightly to prevent sucking up sediment from the bottom. Furthermore, the fluid itself has surface tension and viscosity.
It's like trying to drink a milkshake with a straw.
Yeah,
You can never get that last little bit at the bottom without taking the lid off.
that's a great way to put it. So no matter how hard you pump, you can never get a tank 100% bone dry just using its own discharge system.
All right.
There is always a residual layer of liquid left at the very bottom. That unpumpable volume is the heel. It might be 50 gallons in a small tank or 500 gallons in a massive one. You cannot count the heel as available storage capacity because you cannot operationally access it. It's dead space.
Okay, so we take our total volume, we subtract the steel deadwood taking up space inside, and we subtract the unpumpable heel at the bottom. We finally have our true usable volume.
Almost.
Right, the most terrifying part of this formula is the final multiplier. We have to multiply by a fill percentage.
This is the absolute golden rule of process safety. A volatile liquid tank is never, under any circumstances, filled to 100% of its physical capacity.
But why? If I've accounted for the deadwood and I know exactly how much room is left, why can't I fill it to the absolute brim?
Because you have to leave room for the physics of thermal expansion. Liquids are highly sensitive to temperature. If you have a massive steel storage tank sitting out in the Texas sun and you fill it to 100% capacity with a chemical solvent at 6:00 a.m. when it's cool, What happens at 3:00 p.m. when the ambient temperature hits 105 degrees and the radiant heat of the steel raises the temperature of the liquid?
The liquid heats up, the molecules gain kinetic energy, the fluid literally expands, taking up more physical volume than it did at 6:00 a.m.
And if you filled it to 100%, there is no void space left for that expansion to occupy. Liquids are incompressible. They don't just squeeze together. They exert hydraulic force against the container.
So the pressure inside the tank spikes catastrophically.
First, the pressure relief valves will actuate, and the tank will begin venting chemical vapors directly into the atmosphere to relieve the stress.
Which is bad enough.
But if the expansion outpaces the venting capacity, the hydraulic pressure will literally pop the seams of the steel tank, resulting in a structural failure and a massive liquid spill.
But the sources point out that a spill might actually be the best case scenario compared to the alternative.
Oh, absolutely.
If you overfill a pressurized vessel containing a liquefied gas, something that is normally a gas at room temperature but is being compressed into a liquid state, and you subject it to heat without sufficient vapor space.
You are setting the stage for a BLE.
BLEVE, boiling liquid expanding vapor explosion.
It is the nightmare scenario for any facility engineer. Let's look at the mechanics of a DLFE.
Break it down for us.
Okay, you have a pressurized tank filled with a flammable liquefied gas, like propane. It's filled past its safe fill percentage. An external fire breaks out near the tank, heating the steel walls.
The liquid inside begins to boil rapidly because of the intense heat, increasing the internal pressure massively.
The safety valves are venting, but they can't keep up. The fire weakens the steel shell of the tank above the liquid line. Because you overfilled it, there isn't enough vapor space to buffer the pressure wave.
The tank is basically a bomb at this point.
The weakened steel suddenly ruptures.
And because the liquid inside is superheated, the moment that pressure is released, it hits atmospheric pressure.
The entire volume of liquid instantly flashes into a vapor. It expands to hundreds of times its original volume in a fraction of a millisecond. That violently expanding vapor cloud instantly ignites from the external fire, creating a massive, devastating fireball and sending shrapnel from the tank flying for miles. Historic BLEVs, like the Faison disaster or the Los Alfacres tragedy, have leveled entire facilities and caused horrific casualties.
And the mathematical firewall against a BLEV is the fill percentage.
Yes.
It's the safety professional calculating the coefficient of thermal expansion for that specific chemical, analyzing the worst-case ambient temperature spikes, and mandating that the tank can never be filled past, say, 85%.
That 15% void space is what absorbs the expansion. It's the difference between a normal Tuesday and a catastrophic crater.
The math literally saves lives.
It really does.
What if the math isn't enough? What if a pump fails in the open position, or a pipe corrodes and snaps, or a forklift simply loses control and rams into the side of the tank, puncturing it? We have to plan for failure.
This is where we shift from operational calculations to mitigation calculations. We introduce the concept of the fail-safe, known in the industry as secondary containment.
If you've ever driven past a refinery or a large chemical plant, you've seen these. They're the massive concrete walls or earthen berms built at a perimeter around the storage tanks.
The berm is essentially a giant open-topped rectangular prism, and the safety professional is tasked with calculating exactly how large that prism needs to be to catch the disaster.
The rule for this in the ASP sources is incredibly specific. It is known as the 110% rule. The volumetric capacity of the secondary containment berm must be greater than or equal to 110% of the volume of the largest single tank contained within it.
Let's interrogate that rule because it's a brilliant example of regulatory logic.
Yeah, why 110%? If I have a 10,000-gallon tank and it suffers a catastrophic failure and empties completely, it is going to spill exactly 10,000 gallons. Why on earth do I need a berm that holds 11,000 gallons? It seems mathematically redundant.
It does, until you remember the Archimedes principle and the messy reality of industrial sites. Let's look at displacement first. Rarely is there only one tank sitting inside a massive berm.
Usually you have a tank farm, 3 or 4 10,000-gallon tanks all sitting inside the same shared containment area.
Exactly. So if tank A ruptures, 10,000 gallons of liquid floods the berm. But tanks B, C, and D are still sitting there intact. Their physical steel bases are occupying volume inside that berm.
It's like dropping ice cubes into a glass of water. The intact tanks displace the spilled liquid, forcing the liquid level to rise higher than it would in an empty basin.
Right.
If your berm was mathematically calculated to hold exactly 100% of the spilled volume, but you didn't account for the displacement of the other equipment, the spill is going to crest the wall and escape.
And the second variable the 110% rule accounts for is meteorology. These berms are almost always outdoors, exposed to the sky.
Which means they collect rainwater.
EPA SPCC guidelines require facilities to design containment that can handle the 25-year, 24-hour storm event for their specific geographic region. If you have a severe weather system that dumps 6 inches of rain into your containment berm over a weekend, you have lost a massive percentage of your void space.
The rainwater essentially acts as a pre-existing spill.
Exactly. If your berm was only sized for 100% of the tank and it's currently holding 3 inches of rainwater, a tank rupture is guaranteed to overflow. That extra 10% capacity is the margin of safety engineered to absorb the unpredictability of displacement and weather.
That is brilliant.
Calculating that berm correctly is arguably one of the highest value actions a safety professional takes to prevent a localized mechanical failure from becoming an EPA-level ecological disaster.
Okay, so we have built the physical world, we've navigated the geometry, the unit conversions from cubic inches to gallons, we've analyzed warehouse utilization factors and floor loading, and we've dissected the fluid dynamics and fail-safes of liquid storage.
That's a lot of math.
It is, but there is one final layer we have to lay over all of this.
The legal framework. Because a safety professional doesn't just calculate risk in a vacuum, they calculate it to ensure strict compliance with federal law.
We're talking about OSHA's hyper-specific regulations for the storage of flammable and combustible liquids. The exam requires you to know these thresholds cold because violating them is a criminal offense.
It's not something you want to mess around with.
Let's start with the basics of indoor storage. The ubiquitous yellow steel storage cabinets.
Oh, they are everywhere in manufacturing and laboratories. OSHA mandates a rigid mathematical limit on what can go inside them. You are allowed to store no more than 60 gallons of flammable liquids or 120 gallons of combustible liquids in a single approved cabinet.
We really need to define that difference because doubling the allowed volume is a massive jump. Why 60 for flammable, but 120 for combustible?
It all comes down to the flash point, the lowest temperature at which a liquid gives off enough vapor to ignite in air. Flammable liquids have a very low flash point. They can ignite at normal room temperatures. Think gasoline or acetone. They are inherently highly volatile. Combustible liquids, like diesel fuel or certain heavy oils, have a higher flash point. They have to be heated significantly before they will ignite.
Because flammable liquids are so much more eager to burn, OSHA cuts their allowable volume in half to limit the potential intensity of an accidental fire.
Precisely. But the regulation doesn't stop at the cabinet level. It regulates the macro space as well. The law states that not more than 3 of these cabinets can be located in a single storage area.
Wait, so even if I have a gigantic 50,000 square foot manufacturing floor, I can't just line one wall with 20 yellow cabinets to store all my solvents?
Absolutely not. And the logic behind the 3-cabinet rule is based on limiting the localized fire load. If a fire breaks out in a specific zone of the facility, the local sprinkler heads will activate to suppress it. But standard sprinkler systems are engineered to handle a certain maximum heat release rate.
If you have 20 cabinets of highly flammable liquid clustered together, and they all become involved in the fire,
the resulting thermal column will instantly overwhelm the local sprinkler array. The water will literally vaporize before it hits the flames. By capping the storage at 3 cabinets per area, OSHA mathematically guarantees that the total potential fuel load in any one zone remains within the suppression capabilities of standard fire systems.
and if you don't even have a cabinet, if a worker just leaves a can of solvent sitting out on a workbench.
Highly restricted open storage. OSHA allows a maximum of 25 gallons of flammable or combustible liquids to be stored completely out in the open in a given room. Anything over 25 gallons must be secured in a cabinet or a dedicated room. It limits the ambient vapor risk.
But let's scale up again. What if we aren't in a lab, but out at a major industrial depot or a construction staging site? You have pallets of 55-gallon drums of diesel. You aren't putting those in a yellow cabinet.
For bulk container storage, OSHA transitions from regulating volume to regulating spatial geometry. They dictate the exact physical footprint of the storage. The rule is, storage of containers cannot exceed 1,100 gallons in any one pile.
1,100 gallons.
Yeah.
A standard drum is 55 gallons. So that's exactly 20 drums per pile.
Yes. You mathematically cap the pile at 20 drums. Furthermore, you cannot just push multiple piles right next to each other to save space. OSHA requires that piles must be separated by a minimum 5-foot clearance space. They must be kept at least 20 feet away from any adjacent property lines or buildings.
That 20-foot distance is a radiant heat buffer, right? So if the pile catches fire, the radiant energy doesn't ignite the building next door.
Exactly. But the most critical spatial regulation for bulk piles is the access requirement. There must be a 12-foot wide access way within 200 feet of every single pile.
12 feet wide. That is a very specific, very large number for an access aisle. That's not for a forklift.
No, that is for a Type 1 fire engine. If an 1,100-gallon pile of diesel fuel ignites, you're dealing with a massive incident. You need to ensure that heavy fire apparatus has the physical clearance to navigate the site, approach the fire from a safe distance, deploy high-volume hoses, and fight the blaze without getting bogged down in narrow alleys of stored material.
The spatial geometry of the storage site literally dictates the tactical geometry of the emergency response. If a safety planner ignores that 12-foot access rule to cram in more pallets, they're mathematically guaranteeing that the fire department won't be able to save the facility.
It's a perfect example of math acting as a life safety tool. But there is one final, highly complex OSHA scenario the exam tests heavily. What happens when a manufacturing process requires massive amounts of flammable liquid, thousands of gallons, to be stored inside a building? 3 little cabinets aren't going to cut it.
In that scenario, OSHA requires the construction of what they call an inside storage room, and the capacity of these rooms is calculated using a sliding scale based on fire resistance engineering.
This is where we see exactly how safety investments buy operational volume. The capacity of an inside storage room is determined by 2 factors: the fire resistance rating of the walls and the presence of an automatic fire protection system, like a dedicated deluge sprinkler array.
Let's look at the numbers. Say a company heavily invests in safety. They build a room with a 2-hour fire-resistant construction, meaning the walls and doors can withstand a direct, intense fire for 2 hours before failing, and they install an automatic fire protection system.
Under those conditions, OSHA rewards the safety investment. They allow that room to be built up to 500 square feet in size. And crucially, they allow a storage density of 10 gallons of liquid per square foot of floor space.
So 500 square feet multiplied by 10 gallons, that is 5,000 gallons of highly volatile liquid legally allowed inside that room.
Correct. The math reflects the low risk of the fire spreading beyond that 2-hour sprinkler-protected bunker. But let's look at the penalty for cutting corners. What if a facility manager tries to save money? They build a room with only a 1-hour fire resistance rating, and they decide not to pay for the automatic sprinkler system.
How severely does OSHA punish that lack of engineering?
The allowable limits plummet. The maximum permitted size of the room drops from 500 square feet down to just 150 square feet. And the storage density drops from 10 gallons per square foot down to a mere 2 gallons per square foot.
Wow, let's do that math. 150 square feet multiplied by 2 gallons per square foot. That is only 300 gallons total.
You went from a legally compliant capacity of 5,000 gallons down to 300 gallons, purely because you lost 1 hour of fire resistance and your sprinklers.
That is an astonishing mathematical penalty. It is a 94% reduction in your operational capacity.
But it perfectly reflects the exponential increase in risk. A 1-hour room with no sprinklers containing 5,000 gallons of flammable liquid isn't a storage room. It is a thermobaric weapon waiting to detonate in the middle of a factory. The regulations force the company to either invest the capital into heavy physical safety engineering or radically restrict their operations.
And this highlights the ultimate stakes for the safety professional taking this exam or doing this job. If they miscalculate that room's rating and tell management they can store 5,000 gallons in a room legally rated for 300,
the consequences are total. First, they are exposed to massive, crippling legal fines from OSHA for willful violation. Second, if a fire does occur, the insurance underwriters will instantly void the policy because the facility was operating outside of fire codes, bankrupting the company. And third, they have created an uncontrolled, catastrophic hazard that puts the lives of every worker and first responder in imminent mortal danger.
Which brings us to the grand synthesis of everything we've discussed today, the integrated model of how a safety professional thinks. We've covered geometry, the unit mismatch trap, warehouse floor loads, liquid deadwood and fill percentages, secondary containment berms, and the strict legality of OSHA flashpoint limits. How do we pull all of these disparate physical and legal realities into a single cognitive process?
The QHSE notes provide what they call the final master equation. It is the ultimate distillation of ASP domain 1.
Safe storage capacity equals, open parentheses, geometric volume minus losses. close parenthesis, multiplied by utilization, multiplied by safety limits.
Let's run a final scenario through that master equation to see how it acts as a step-by-step cognitive checklist. Step 1, geometric volume. You identify the correct shape of the real-world object and apply the math. Is it the pi r squared of a cylinder or the length with height of a berm? You establish the physical bounds.
And crucially, you execute the unit conversion here. You take those cubic feet and you multiply by 7.48 to get your baseline gallons, so you're speaking the language of the law.
Exactly. Step 2, you subtract the losses. You must account for the mechanical reality of the space. You subtract the deadwood of the internal piping. You subtract the unpumpable heel at the bottom of the tank. You reduce the theoretical volume down to the actual void space.
Step 3, multiply by utilization. You apply operational reality. You multiply your warehouse volume by a 0.7 utilization factor to ensure your aisles are clear, your sprinklers are unobstructed, and your workers can escape a fire. You apply your safe fill percentage to your chemical tank to guarantee it has enough void space to absorb thermal expansion without causing a BLE.
And finally, step 4, multiply by safety limits. You take that final, highly refined number and you cross-reference it against the rigid legal framework. Does this weight exceed the PSF floor loading limit? Does this volume of flammable liquid exceed the 10-gallon per square foot limit of my 2-hour fire room? Does this tank require a secondary containment berm calculated at 110% of its volume?
When you lay it out like that, it becomes incredibly clear that mathematics in the health and safety profession is essentially a crystal ball.
If we connect this to the bigger picture, that is exactly how I view it. It is predictive modeling.
It allows a single professional sitting at a desk with a set of blueprints and a calculator to foresee the future. They can look at the math of a concrete slab and foresee a structural collapse 5 years down the road caused by a 0.3 shift in specific gravity. They can look at the thermal expansion coefficient of a liquefied gas and foresee a devastating explosion.
Right.
And because they can foresee it in the math, they can prevent it from ever manifesting in the real world.
Anyone with a high school geometry education can calculate the volume of a cylinder. A safety professional's job is to interpret the consequence of that volume, apply safety margins against the chaotic variables of the real world, and defend those margins against operational pressures.
So what does this all mean? We have covered a massive amount of highly technical ground today. We started by stripping away the illusion of abstract math, proving that squaring a radius geometrically explodes your risk profile. We navigated the treacherous unit mismatch trap, where understanding that 1 cubic foot equals 7.48 gallons is the difference between a safe facility and an EPA disaster.
We explored the cardiovascular system of the warehouse, understanding why a utilization factor of 0.7 is a required fire break, and how a subtle change in the specific gravity of a liquid can translate into a crushing floor load that brings down a building.
We dove deep into the chaotic fluid dynamics of process safety, stripping away the deadwood and the heel to find a tank's true capacity, and realizing that the fill percentage is the only mathematical barrier preventing a catastrophic BLAV. We saw how the Archimedes principle dictates the 110% rule for secondary containment. And finally, we locked all of that physics into the unyielding framework of OSHA law, seeing how fire resistance ratings dictate down to the gallon what can be stored safely indoors.
It is a vast, deeply interconnected web where physics, civil engineering, fluid dynamics, and federal law all converge on a single point, keeping the facility and the people inside it safe.
And to you, the listener, whether you are aggressively studying to pass your ASP exam or you simply wanted to understand the hidden structural and mathematical forces that govern the modern industrial spaces we rely on every day, I want to thank you for taking this intense deep dive with us. You are now armed with the conceptual tools to look at the physical world entirely differently. You won't just see a warehouse or a tank farm anymore. You will see fire loads, utilization factors, thermal expansion, void spaces, and floor loading limits.
You will see the math that is holding the physical world together.
Exactly. But before we sign off, I want to leave you with one final provocative thought. Something to mull over as you think about where the industrial world is heading. Throughout this deep dive, we talked extensively about the utilization factor. We discussed how we are legally required to leave 30% of a warehouse empty, the aisles, the turning radiuses, the egress paths, because human workers need space to operate forklifts safely, and they need a clear path to run if a fire breaks out. But look at the bleeding edge of the modern supply chain. We are rapidly transitioning to dark warehouses. These are massive logistics centers where human beings never set foot on the floor. Autonomous robotics, guided by AI, do 100% of the picking, sorting, and storage. These robotic systems don't need 3-foot human egress aisles. They don't need emergency exit doors because they don't breathe smoke. They don't need lighting. The storage densities in these dark warehouses are skyrocketing as automated. Three-dimensional grids packed in tighter and tighter, literally inches apart. So the question we have to ask is this: as autonomous systems completely remove the human element from the storage equation, will our traditional human-centric utilization factors of 0.7 to 0.9 become obsolete overnight? And if corporations are legally allowed to pack these massive spaces to 95 or 99% capacity to maximize their geometric efficiency, will the sheer hyper-concentrated mass of these incredibly dense automated systems push the physical floor loading limits of our concrete and steel to the absolute breaking point? Are we engineering a future where the math of our operational efficiency finally outpaces the math of gravity? The next time you are driving down the highway and you see one of those massive windowless distribution centers rising up on the horizon, just remember, the most important thing inside that building isn't the millions of products on the shelves. It's the invisible calculations straining to ensure the roof stays up, the floor holds firm, and the modern world keeps spinning.